I'm glad you made it to the last bunch of sessions of the Yerevan Data Fest, and I'm grateful you are here. So this talk and all of my work in NVIDIA is devoted to making the life of our customers easier and making them happier with our hardware and making their code run faster on our GPUs. And this talk is a very broad overview of bag of tricks one has to use or can use during his journey of making his or her models optimal and fast on GPUs. And first of all, I guess all of you know that NVIDIA is producing hardware, but nowadays our investments in software are twice as high as investments in hardware. So we are becoming more and more software company. And this slide just demonstrates how many of software products are GPU accelerated. And just as a background, which I guess most of you know, GPU has a lot of cores, but they are simpler than the cores of CPUs. GPUs have thousands of cores and some tensor cores, specifically for the mathematical operations. We will talk about them a little bit later. So one has to re-architect software a little bit so that it runs efficiently on the GPUs. And this is done mostly by NVIDIA engineers. And in this slide, you see the software which has already been re-architected. And today we will be talking mostly about the relevant frameworks on the data science level. And these are, of course, PyTorch and TensorFlow. It's important to understand that there are quite a few layers below them, like Nickel, a library to implement the distributed learning and the communication between different nodes and different GPUs. And there are some levels above, also accelerated by NVIDIA. TAO Toolkit, which got it to the title of my talk, is one of them. And today we will be talking mostly about software, I think only about software. Yeah, and my idea of this talk is just to have this TAO Toolkit, the name of which I will be pronouncing a lot during this session, and have it as an example of these tips I will be giving on how could you accelerate your own neural networks and your own code. And let's begin with what TAO Toolkit is. It's a part of the bigger umbrella brand which is called NVIDIA METROPOLIS, and this is basically all we have for IVA developers. IVA stands here for Intellectual Video Analytics, and this is like all the things you need to get the video from your camera, processed by your neural network, and to then produce some business results. This is the target of the METROPOLIS framework, and you see it's has TAO inside, but it also has DeepStream. I will devote a couple of slides to it. But mostly, for inference, I will focus on TensorRT and TRITON. And I will be taking your feedback along the presentation, like how well you know the frameworks. Do you know about that? Let me first give you a short introduction to TAO. Finally, TAO stands for Train, Adapt, Optimize, and this is what you basically always do with your models. You take some pre-train, if it exists in your scale, and for computer vision tasks, which TAO is originated from, there is usually quite a good pre-train of sizable and good pre-train. And you introduce your own data to tune this pre-train so that it adapts to either your camera or your task, or basically you can have the backbone and make it solve any other object detection task. And TAO Toolkit is just an application which wraps this basic training cycle into the command line interface so that even the beginner data scientists could use that. And why is it an example of my today's talk? Because it does that optimally in many levels. And we'll discuss this during all the next parts. I was talking about computer vision in TAO, but it also has now parts devoted to speech AI, to conversational AI, mostly about speech recognition and speech synthesis training, which is also easily done there. This slide shows the available features for computer vision models. TAO supports all the basic backbones one needs, and all the basic heads for object detection, for image classification, and for image segmentation. So one can easily train them effectively with TAO. But apart from that, TAO is go-to software if you need one of the specialized computer vision models. And TAO has quite a few of them. If you are interested in detecting people and interacting with people, then there is, of course, people detection models, gaze detection models, pose detection models, segmentation models, even heart rate detection from videos. And you can just basically take it for free, run it for free, and build your commercial projects on that for free. This is the value of TAO Toolkit. And there is also a domain of neural networks which are devoted to cars and like detecting the cars as an object, detecting the make and the model of the car from the picture. And this is also a domain which is well covered right now. And just to give some more numbers, TAO has these models implemented to the state-of-the-art level, so that if you retrain them on a rather good data set, they keep being state-of-the-art, which is quite nice. And you can see that in the upper graph. But in the lower graph, there is one more important thing. This is the performance NVIDIA has measured for different models from TAO on different hardware. And this is both hardware which is widely used for inference, mobile GPUs called Jetsons, and our current flagship A100, just for reference. And the reference of the performance will be one of the important things here. This is another slide on the quality of the TAO training cycle. You are able to reproduce the training from the papers with TAO, achieving state-of-the-art or sometimes surpassing that. So TAO has pretty good training cycle, but what else does it have? What is the pipeline of using TAO? You, of course, start from the left, from the pre-trained model, and from your own data. But then, to train efficiently, you have, in the end, to be able to export your model as small as possible and as performant as possible, without sacrificing too much accuracy. So, the things one can do here are the following, and one should do. One should reduce the precision of the numbers to achieve this balance. Or one can experiment with that at least. And if one reduces the precision of the numbers from P32 to int8, let's say, so from 32 bits in the number to 8 bits in the number, one has to introduce some changes into the training procedure. This is called quantization-aware training. There are some implementations of that out of TAO, but TAO has quite a nice one. And there is also one technique which I see sometimes implemented in the wild, but which is actually very rarely for me to see in the wild. It's called pruning. And pruning is, I guess many of you know, is taking out the layers or reducing the dimensions of the tensors inside your neural network, so that you can actually reduce its size. And size reduction, as we will see, gives you some benefits in the performance as well. And pruning is implemented in TAO as a basically command line switch. this is a useful feature of TAO, and why I think TAO can give you quite a reasonable baseline for your computer vision task, especially if you are balancing between performance and accuracy. And yeah, this is basically all the diagram. One more thing, augmentation of the data. You have to do it, but you have to make sure there isn't a bottleneck in that, because otherwise you are not utilizing the GPU completely. So, I've already explained how TAO is built, like what are the building blocks of TAO. It runs, of course, trains on all the GPUs, be it the server GPUs, be it the gaming GPUs, but usually there is a support for the multi-GPU train and multi-node train, which is often happens only in the enterprise environments. And for deployment, the small modules, low power consumption, that Jetsons are supported. And as an interface, TAO uses Jupyter notebooks, familiar to all of you, so yeah, you can easily play with that. At the end of each section, I have the links. I will skip them, but after that, you can follow them. So, the first and the thing I'm advocating most, even for the researchers, which TAO uses extensively, is containers. Let's give a quick check. How many of you do use containers for deep learning training?
Especially NGC or NG?
Especially NGC, but that's the next step. Very few actually. So, what's the value of containers? I've already told you that the modern deep learning stack is a bunch of libraries, and these are just some of them. And if one wants to make sure that all these libraries in the stack are compatible, one has to test them together. And that's what NVIDIA does. We do build containers with all these libraries in a joint bunch, and we test them together. And that brings all these dependencies into the container. The host has to have only one thing, three things, sorry. Spanish Inquisition came here. The host has to have its open operating system and some GPU driver. And the host has to have Docker engine with NVIDIA container runtime. And that maps the driver into the container. And if you are running the enterprise grade GPUs, you are even able to run the containers with the newer version of the driver, which require a new version of the driver on the older driver on the host. This is called CUDA forward compatibility, and this is important mainly for enterprise environments. And we are not only building these containers, we are publishing them on our hub, which is called NGC. It's a repository of containers. You can use them for free, both in commercial and personal use. And we encourage you to use them even if you have your own tiny GPU machine with one, 1080. Please use containers. That will make your life easier when you will move to another machine. It's very easily reproducible between the machines, and you can bring it from research to production in a smooth and reliable way. Other than the containers, which of course exist for PyTorch, for TensorFlow, and for TAO Toolkit, which we were discussing, and they are discussing, there are also models stored on the NGC, and the models I have been describing from the TAO Toolkit, they are actually in the background downloaded from NGC. A little benefit of the containers I haven't mentioned yet. they are able to run both on-prem, on your tiny, lovely machine, or in the cloud if you are a startup and you would like to scale your training. That might make sense, by the way, scaling the training. And you use the same container for that. Why should one use containers from NGC and not from Docker Hub? Because our engineers commit to the deep learning frameworks, to PyTorch and to TensorFlow. And these commits are faster to appear in the containers. And these commits allow one to speed up the training of his or her neural network. In this slide, if you compare the left two bars in each category, that's the speed up one gets just from changing the container 5 months ahead. And this is like 20% faster training, 20% of cost savings on your training in the if you switch the container. And this is significant. Why wouldn't you save on that just by changing one number? It's a trend that continues, and that's why we suggest using NGC containers. The one comment that these updates get to the master branches of the frameworks, of course, but that happens later. It can be delayed by the long review process. So, the first part is I hope that everybody who is in this room training his or her own neural networks will start doing this in the container. It's much easier and like.
Are there also containers for Keras?
Yes, there are containers for Keras, I believe. Nowadays, Keras is a part of TensorFlow, isn't it?
It's a long time that Keras is so.
Yeah. So there are containers with TensorFlow, and they do include Keras, of course.
No, I mean the Keras and the Keras that is inside the TensorFlow has some differences. So
there's a special container for Keras.
Yeah, there was at least when I last checked.
Already duplicated.
Yeah. Another quick comment on the containers. They are compatible with most IDEs nowadays, and especially VS Code. I use it and I like it, that's why I know how to do it. You can set up a container as your remote environment, even if it's the container running on a remote server. So you can just log in to that container with Visual Studio Code and basically enjoy that environment with full code completion, debugging, everything. That works, and that's very nice. So containers are the must. The first, top one thing to use for training. Top two thing to improve your training happiness, and actually inference happiness, is tensor cores. How many of you do know what a tensor core is? Okay, but that's quite a number. What is important to know about tensor cores is that these are hardware accelerators for matrix multiplication. And another important thing is the less the size of the number in the matrix, the less the precision of the number in the matrix, the faster the tensor cores work. So let's say for int8, they're twice as fast as for FP16. And for FP32, there are some generations of tensor cores which do work with FP32. They're twice slower than for FP16. So that means if you can reduce the precision of your data, of the weights of your matrices you are multiplying, do that, and that will gain you quite significant speedups. Another important thing is that you don't like to lose the precision when it's most critical. And during the training, it's most critical in the gradients. The gradients, and it is possible to have the following setup, which is called mixed precision training, when the weights of your matrices are in FP16, and you accumulate gradients in FP32. This is called mixed precision, And there is a way to implement it automatically. But for now, let's just summarize the value of mixed precision training. So you use tensor cores to accelerate your computations. That gives you a huge boost in performance. And nowadays, the most boost in performance you can get for your neural network is from tensor cores. So your performance heavily depends on how efficiently do you utilize tensor cores. This is one of the biggest factors of you should track. And how does the speed up happen? Apart from the max speed up, which I've already described, and for some generations, it's an 8x speed up CUDA cores versus tensor cores. You already, if you use FP16, you halve the memory traffic because the weight of your neural network decreases in size by 2. And you halve the memory storage. And by halving the memory storage, you can increase the batch size to fill the GPU back so that you utilize the whole memory. And you introduce even bigger increase in the performance like this. So this very significant, the first step to try if you are thinking about optimizing your training, mixed precision training. And I will skip this slide or talk a little bit about it. For the newest generations of GPUs, Ampere and Hopper that is, one can use FP32. These precisions still utilize tensor cores, but do it with the reduced accuracy. But if you can switch to FP16, please do that. And I was describing the value of mixed precision. It's also very easy to opt into that because there are automatic mixed precision tools for all the major frameworks. And like it's a couple of lines in PyTorch, it's one line in TensorFlow, even Paddle and MXNet, which are less popular in the European part of the world, they do support that, just because that's that valuable. Links, next part. I was already telling you that it's important to have the reference of the performance. And it is indeed the number which can tell you, is your neural network fast at training, or do you have some bottleneck? Because if you have a reference published by, for example, by NVIDIA, that, okay, we are able to train, let's say, DATACENTER in 99 minutes on this number of GPUs, and your implementation trains in, let's say, a day on the same number of GPUs, then you know something's completely off. And you know the references are useful, and more importantly, these references are from the composition which is called MLPerf. It's Grigory Semenov has mentioned it yesterday. It is an industry standard benchmark designed to compare the hardware for deep learning apples to apples. And NVIDIA is usually the best in all the categories. We always submit in all the categories and win all the suit. So there is a code to reproduce them. They are reproducible and valid. So use them as a reference. And there is another bunch of references for your performance, just to track if you are getting what you expect, what you should expect. This is called the deep learning examples. This is just a GitHub repository with open source implementations, reference implementations of multiple neural networks in many domains, including, of course, CV, NLP, speech recognition, recommender system, speech, text-to-speech, NLP, all that. And you will be able to follow the links in the slides. They also have nice features regarding multi-GPU training available, and deployment options available. And I will share that, talk more about deployment later. So, the third common bottleneck I've been able to observe as a solutions architect at NVIDIA is the bottleneck during the data preparation. And we have a special library for that, for some cases. It's called DALI, or NVIDIA Data Augmentation Library. And this is basically what it says. It's a library which implements effective augmentation and effective data loading. So you can use it as a data loader in PyTorch, you can use it as a data loader in TensorFlow. It does it in a nice parallel way. It introduces a lot of workers. Of course, you can implement the parallelizable data loading in PyTorch yourself, but people often forget to do that. Really, that's why using DALI is easier. One side note: sometimes it may be even feasible to use data augmentations on GPU, because at some operations GPU is much faster to implement that. And DALI has this capability. But basically, if you are augmenting your data on the CPU, DALI also has this capability and also speeds up the training. And yeah, these were the three most common solutions to most occurring problems. But then goes the deeper part. If you've implemented all the three of them and you still don't know what to do to improve the performance, you have to go to profiling. And GPU profiling is not that hard. I have a full talk on GPU profiling on DataFest 2020. It's recorded, and because it was a COVID DataFest, and it was online. I'm, by the way, very happy to see real faces on this talk. There is a tool which is called Insight Systems, NVIDIA Insight Systems. It is a go-to profiler for any GPU code, and there's one more name one should know. The name is NVTX, and NVTX is a library which allows you to annotate your profile of the GPU. So you can annotate the segments of your code. Let's say you can emit the command, this is the beginning of the segment which I call, let's say, validation. And then this is the end of the segment which is called validation. And then in the graphical interface, you will see the segment which is called validation. And that allows you to easier understand what is happening easier correlate your code between and what is happening in the GPU. So NVIDIA is important thing to know. And this slide is also the slide where I would like to explain why I think how should you approach the optimization of your code. So if you would like to completely optimize that, for example, if you are running the large language model and your training takes a lot of time, then the GPU is your second most precise resource. So there is a balance. What is your most precious resource? Is it people or GPUs? And you have to make sure you use both of these resources efficiently and effectively. And for GPU to use the GPUs effectively, you have to make sure they are 100% utilized all the time, and that everything the CPU can do simultaneously in parallel with this GPU utilization, that it does it. A couple of other tricks from the other talks. There is a very nice talk on our conference G2C 2021 on tips on PyTorch. It's a little bit more in depth than mine. So here's a link. If you are starting a new project in PyTorch, it might make sense to use PyTorch Lightning because it provides some sensible defaults for the training. And especially if you are considering multi-GPU and multi-node training, PyTorch Lightning there has a pretty nice interface. And of course, you may say, we are a small startup, we cannot afford the multi-node training. But actually, the scalability of current deep learning workloads is pretty good. So money-wise, training the model for a week on one GPU and training the same model for a day on 8 GPUs may be similar, but the iteration time is much quicker if you have multi-GPU and multi-node training. So using the GPUs, using multiple GPUs to train your model, you may increase the efficiency of usage of your most precious resources, employees. So yeah, consider using multi-GPU and multi-node training. This is especially in the cloud when you are not limited. This was all I would like to tell you about training. Now I have cut off 10 minutes to tell you about inference. So let's start from the basic question. How many of you know what TensorRT is? Okay, let me explain to the other half of people. Basically, TensorRT is an optimization compiler for neural networks. It takes one neural network, so you give it your one neural network, and it optimizes all the implementation of it in the backend, and the result of application of TensorRT to your neural network is what we call an engine file. It computes your exact neural network on this exact hardware where you have been running TensorRT in a very efficient manner. And by very efficient, I mean gains of 10x, I've seen that's fine, 3x, so several times faster than the original code. That's the basic idea of TensorRT, the basic value proposition of it. But how does it do it? I've suggested to tell some more deeper insights into that. First, it uses mixed precision. I've already talked about that. And TensorRT does implement reducing the precision both inside the network, keeping the inputs and outputs in their original precision, and also you can even tune it to int8 and have the special calibration cache as a part of your deployment, so that your network keeps its accuracy in the int8 mode. Second idea is a little bit more about the hardware, and this is layer and tensor fusion. This you can also implement yourself if you would like to, but what it is, imagine you have two similar layers in different branches of your neural network. If the implementation is basic, then you have one CUDA kernel for this branch, and another CUDA kernel running for another branch. And they compete for resources, and they do it in sequential mode. But if you introduce layer fusion, then there is one CUDA kernel which is run. There is much less overhead to managing these CUDA kernels and managing the data. And that's one of the ways TensorFlow optimizes the execution under the hood. Another thing, of course, is choosing the best implementation for your mathematical operation. There are, I guess, more than dozens of implementations of convolutions in the GPU. Like, there could occur more than dozens, could occur kernels which implement the convolution. And which one is the most optimal? It depends on the parameters, on the dimensions of your layers. And TensorRT just launches them, measures the performance, and selects the most performance. Another thing there is that also there are optimizations of memory usage implemented that you can do yourself, but they are already done in TensorRT. If you are developing some new neural network with research layers that is hard to convert to TensorRT, then there are frameworks called Torch TensorRT and TensorFlow TensorRT. TFTRT is even the part of TensorFlow. And what they allow you to do is convert only the subgraph of your model, which is supported by TensorRT. And that allows you to combine the best of both worlds. You keep your novel layers, and you get the acceleration for inference. And as a result, you can save the model as a legit torch script file or saved model for TensorFlow. And these models are the ones you are used to if you do inference in these frameworks. So these frameworks make it very easy to compile your models. Basically, one line in Torch, one line in TensorFlow.
But it's only for FP16.
FP16 as opposed to
If you want to have the one line code, it's only the quantization for FP16.
Yeah, okay.
If you want to make the int8, you will suffer a bit.
That's true. There is an API for int8, and it's a little bit more tricky. That's true. The basic way is to convert the whole neural network as an ONNX file, which is an open standard, to the engine. And yeah, it's technical. There is one more thing in TensorRT. It's a little bit experimental. It's sparsity support. It's another way of pruning your neural network. TensorRT supported sparsity, where 2 of each of the 4 weights is 0 in a row, and you have to use the special library which is called Apex to achieve that. Feel free to experiment with that if that may help you. So TensorRT is widely used. It's used by Hugging Face. It's used by us to submit all the MLPerf tasks. And that's a short point. Another one, that if you are unhappy with how TensorRT performs, you can modify it. You can introduce the plugins for your special layers and implement them yourself as a CUDA kernels and beat the TensorRT in performance. So that's it about TensorRT. To recap, like if you have a neural network, you are going inference, just convert it with the TensorRT, and the inference will be much faster on the GPUs. The last piece, I hope it's the last piece, of my today's talk is TRITON Inference Server. It is a higher level than TRITON. It is a microservice for managing your resources for inference. The idea is that on a hardware server with some GPUs and a CPU maybe, of course, you run one instance of TRITON, and then you tell it, you give it a pointer to your model repository, and you configure it how many instances of each model on which GPU would you like. And TRITON helps you deploy them and then do a real-time inference on them with lowest latency possible, with very high throughput, and this models will support simultaneous requests and simultaneous processing. And as a microservice, of course, as you would expect, Triton can be used as a container, and it can provide its metrics to Prometheus. So you can easily integrate it to auto-scaling or to load balancing. And what's important about Triton, it's open source, so you can examine the code thoroughly, and you can tune it to your own task, and things like that. How does Triton achieve this balance between efficiency, between latency and throughput? Well, the most basic thing Triton introduces is dynamic batching, and it takes the query from either Python or C++ library, or a Java client we have now. It sends it to the dynamic batcher. The dynamic batcher builds a batch of the preferred size for the model, be it 4 or 8. And could anyone guess why the models can have the preferred batch sizes?
Because the scale between the batch size and the inference speed is not linear, and it's not even close to be linear.
That's a good answer. And another point of view on that is that the part of this nonlinearity between the performance, between interdependence of performance from the batch size is caused by the tensor cores. They operate best when your matrix sizes are divisible by 4 or by 8, and this introduces spikes. Yeah, but actually 4, yeah. So this does introduce spikes. This is why your models might have preferred batch sizes. These batches we have built in the batcher are then sent to a backend, and what's important here is that Triton supports all the backends you may be using for inference. It supports PyTorch, it supports TensorFlow, of course it does support TensorRT, it supports Onyx runtime, it supports even OpenVINO to accelerate your inference on CPUs. You may use Triton if you have no intention of using GPUs at all. Triton is capable of running all the models on CPU, and even outperforms Intel's own submissions to MLPerf for some magical reason. All this happens with the models which are loaded from the repository. It's just a folder, and you can upload newer versions of the models into that folder, and Triton will update them on the fly. And yeah, the metrics below are shared to the Prometheus. One more thing is that if you have your own inference engine already implemented and somewhat tuned in languages like C or Java, then Triton can be loaded as a library and linked to as a library, not as a container. And you may use Triton as a library to get all the benefits of it. But sometimes I often get asked, what is the key feature of Triton that we can't implement ourselves? Well, every separate feature of Triton is rather easy to implement, but the key benefit of Triton is that it's able to run all the models from all the different frameworks in all the scenarios, be it CPU running, GPU running, on-prem, in the cloud, or on Jetsons. Bare metal hypervisor, containerized, virtualized. It supports batch inference, it supports real-time inference, it supports streaming inference, which is important for speech recognition and synthesis. And it does all that maximizing hardware utilization. So this combination of all the features that's hard to implement yourselves, because it takes time for each of them. This is a slide 3, I will skip that. Triton has quite a few open source examples you can start from. There's also a quick start example. Feel free to follow the links to the docs. No, Triton wasn't the last. There's one last optimization I would like to tell you about. This optimization is specific to video analytics. So let me ask you, are you working on video analytics, like processing the videos from cameras? Is there anyone? Okay, so for 2 of you, a special dive into one optimization. Having to work with video, there are many operations you do in a pipeline. You get the video through the network, you decode it with the codec, and then you pre-process it and batch it, and only then you do infer your neural network. And all these operations can be hardware accelerated, and that's what one should do, especially for decoding and encoding of the video. There is a special accelerator on the GPU which is called NVIDIA coder or NVIDIA coder. And make sure you are using that if you are working with video and it's decoded. And another last optimization I will mention. I hope this is the last one. Is buffer sharing. So avoid copying the tensors as much as possible. And in the context of video analytics, it's harder than it looks, because you have to pass the same memory through the different modules, through the different modules. And there is a special architecture which is called circular buffer, which is implemented in DeepStream. And if you are into video analytics, DeepStream might help you by having these optimizations already implemented. DeepStream is quite a deep framework and it has quite a lot of links. Yeah, and this was the last. That's true. So now only the 2 recreational slides. This September, from 19 to 22, we are having an online conference, GPU Technology Conference, or GTC. It is free, it is completely online, and there are definitely talks about accelerating or improving somewhat on exactly your topic for each one of you, because there are hundreds of talks, literally. Feel free to register, because it's a free registration, and watch the keynote to understand like what the GPU world will look like in the next couple of years. I've told you about TAO Toolkit as an example of the efficiently built model training pipeline. And then we've dove into some key components that make it faster. We've covered containers, we've covered mixed precision, we've covered tensor cores, and then we've switched to inference, where we've covered how could one optimize his model for inference and efficiently serve that with tensor, and TRITON. That's it. Guys, we've made it to the end of the last session of the DataFest 2022 in Yerevan, and I'm grateful to organizers, so let's give them a big round of applause, because this DataFest. Yeah, and now I'm open to take the questions and comments.
For the data loader that you mentioned, Dali,
Is it different from PyTorch in terms of those data load, in terms of like efficiency?
Yes.
Or it's just a wrapper?
Yes, it is. So what they have implemented there are the specific loaders for the specific data types. So for example, if you're working with images, there is a special optimized JPEG decoder and a way to load the data from that. And also the PyTorch data loader doesn't have in itself the opportunity to implement the augmentations. You usually do augmentations a little bit after, or like you need to be knowledgeable to implement the augmentations effectively inside the PyTorch data loader. And DALI has this implemented. The formats which DALI supports include audio and video, which are tricky formats to load sometimes, especially if you need a small part of the audio, a small part of the video, then there has to be some seeking implemented to seek to the proper second of the audio file, and DALI has this implemented.
Does it also support any open source augmentation libraries?
I think DALI, the goal of DALI is to implement the augmentations themselves. They have quite an impressive list of implemented augmentations, honestly, and the value is that they do implement it in a very efficient manner. They do optimize the augmentations as much as possible.
Thank you.
Yeah, go ahead.
Yeah, the continuation of this PyTorch integration.
Could you speak a little bit louder, please?
Yeah, sure. When the DALI loads the data from hard drive, does it directly load to GPUs if there are?
Got it. So the thing you are talking about, directly loading the data from the hard drive to the GPU, is called GPU direct storage. And there are also, so this is one part, one option, and another option for GPU direct storage is to load the data directly from NFS storage or network file storage to the GPU without the CPU cycles utilized. And I think, like, I've checked a year and a half on that question exactly, and DALI was to implement it in half a year. So if all went well, it is already implemented in DALI for already a year. But yeah, you can check following the links. The technology you are referring to is called GPU direct storage. Okay.
My question would probably be about TRITON framework. So about a year ago, I had like some experience of trying to build a production setup with this, and basically I ended up being my own shitty DevOps with like a lot of Python scripts to like load the models and automate these parts. I'm kind of curious, did anyone take care of actually integrating it to all of the like popular orchestration tools like Airflow, Kubeflow, like or any other like DevOps automation?
Yeah.
Because it wasn't there.
Yeah, a great question about TRITON integration into orchestration tools. So first of all, it is built around Kubeflow API. So there is Kubeflow Predict API version 2, and it's the API that TRITON is built around. There are nowadays a lot of integrations of TRITON into the MLOps solutions. I wouldn't name too many because I don't remember them from the top of my head, but one is Dominos, I guess. Another one is Run AI. That's the two I do remember, but of course TRITON is also integrated into the orchestrators in the cloud. There is an Azure integration, I believe, and AWS integration. There was also announced a product which is called, I think, TRITON Load Balancer. As far as I checked, it is still being developed. So there were no announcements about it.